Good afternoon, everyone, and thank you for joining Hosokawa's webinar on Dry and Wet Sieving Technology for particle size analysis. My name is Tim Calvo, and I am the Laboratory Equipment Product Manager here at Hosokawa Micron Powder Systems. Hosokawa Micron Corporation is a global leader in powder processing equipment and systems with its headquarters in Osaka, Japan. We employ over 1,500 employees worldwide and have production facilities in 5 countries. We additionally have 12 technical centers and research facilities. Hosokawa Micron Powder Systems was founded in 1923 under the name of Pulverizing Machinery. We design, manufacture, assemble equipment for size reduction, classification, mixing, compaction, and lab analysis in North America and South America. Our equipment is designed for chemical, food, pharmaceutical, mineral, cosmetics, and plastic industries. We have a research and testing facility complete with an analytical laboratory at our Summit, New Jersey office, where we encourage our customers to participate in the equipment trials and system evaluations. At this time, I'd like to introduce our presenter, Leah Campbell, our Laboratory Equipment Product Specialist here at Hosokawa Micron Powder Systems. Leah?
Thank you, Tim. Welcome, and thank you for joining us today. Today, we'll be discussing particle size distribution and the importance of particle size analysis. Too frequently, customers who own milling equipment are not measuring their particle size, nor do they know their particle distribution range, their particle size range. They're over milling their product and having to restart the process because their material is too fine. This is energy consuming, time consuming, and it's wasting their money and resources. Particle size distribution is designed to determine information about the size and range of particles in a material. We use particle size analysis to help determine the particle size distribution. One mathematical model for particle size distribution is the log normal distribution. This is a single-tailed analysis where we look at the x-axis and the y-axis and we determine the particle size. Another mathematical model for particle size distribution is the Rosen-Ramler distribution. This is a well-known, well-accepted method that uses 2 known points. This is useful for determining variable points of information like the diameter at the 97th percentile, the mean, or the mode of the particle size range. Knowing and controlling the particle size present in a material is important in every step of the process, from incoming raw material to product processing and handling to confirmation of the final product and everything in between. Industries rely on particle size analysis to produce accurate, reliable, repeatable results to save them time, money, energy, and resources. Measuring the particle size, the distribution, and the shape, and understanding how it affects your product and processes can be critical to the success of any manufacturing business. The particle size distribution is not uniform. The powder can segregate according to particle size, particle shape, and thus this affects the bulk property of the material, the flowability and floodability of a material, the stability of the material. Does it change behavior as it goes through the process and handling stages? These effects may result in inaccurate dosages and inconsistent performance. Sieving has been around since the ancient Egyptians. They used to grind and mill their ingredients for bread. They would sieve out the fines, and the coarse material that was retained on the sieve, they would grind and mill again. It's considered the backbone of particle size analysis. The technology for pneumatic dry sieving was developed in the mid-60s as a more accurate method of particle size determination. And over the years, like technology, the equipment has evolved to meet current demands. Wet sieving was developed for materials with a special characteristic. Some materials must be analyzed in a wet state. and other materials present difficulty being analyzed in a dry state. Two methods and techniques we'll be focusing on today is pneumatic sieving and wet sieving. Different companies and different industries require a different range of particle sizes. These two technologies will help test and analyze to make sure they're achieving the range that they require. Aerodynamic sieving principle, also known as pneumatic sieving. This is where a positive flow of air is introduced upwards through a rotating wand. This rotating wand is located directly below the sieve screen. As the wand rotates, it distributes and disputes the sample, allowing 100% of the sample to come in contact with the sieve screen. As the sample comes in contact with the sieve screen, the smaller particles, which we also refer to as fine particles, will pass through the sieve screen. The fine particles are separated by a negative air pressure, which will carry them through the sieve screen and down to the vacuum. A frequently asked question we get from our customers often is, can results from air-jet sieving be compared to shaking or oscillating? And no, they cannot be compared. This is because we work with one screen at a time when using an air-jet sieve. We always start with the finest screen first. When you are using a shaker or an oscillating machine, you use multiple screens at a time, and you start with the coarsest screen and the fine screens at the end. When you remove the fines first, you're eliminating any potential for agglomeration or cohesive material to stick together. This is a problem that often can occur with shaking or oscillating and can skew results. Before sieving, you will weigh the test sieve screen, weigh the sample, and begin sieving. This, you can see here, is an example of the test sieve screen with the sample on the unit itself. During the sieving process, the rotating nozzle will direct the airflow to dislodge and deblind any particles that may be stuck in the sieve screen. You can see the airflow here that the wand is creating, pushing the sample across and distributing the sample around the sieve screen so that the fines, or that, well, at least 100% of the sample can come into contact with the sieve screen. Air is the only force that comes into contact with the sieve screen. There's no mechanical intervention. As the air continues to disperse the materials, you can see that the coarse materials here in this picture is the ones that are retained on the sieve screen, while the smaller particles and the fine particles have passed through. This is an up-close picture of the rotating wand, and as you can see where the red line is, it's where the air comes out of, creating that upward airflow that disperses and dislodges any particles that might be stuck in the sieve screen. Common dry sieving materials: powder coatings, sugars, gypsum, pollen. For us ladies in the industry, any bronzer or any kind of powdered makeup, this is an example where particle size plays an effect with the appearance of the overall product. And we know clumpy makeup is never a good look. Four operational parameters that Hosokawa uses to ensure reliable, accurate, and reproducible results. We need a defined, repeatable sample size. Sieving time. We suggest anywhere 1 to 3 minutes per screen. The more sieve screens used, the more accurate the results. Vacuum pressure. Anywhere between 8 to 16 inches water, the finer the powder, the higher the vacuum pressure. The most important operational parameter is the integrity of the sieve screen. This is something that we will touch on later on in the presentation. The Mikro air-jet sieve, also known as the MAJSX, has many benefits to it. The highly reproducible rates. This goes back to the 4 operational parameters I just listed previously. The more uniformity the 4 operational parameters have during the analysis, the more reproducible rates you will achieve. Time and energy saving. Other methods might take a little bit more longer getting those accurate, repeatable results that pneumatic or dry sieving achieves. This is why pneumatic sieving was created in the mid-60s, was to produce accurate, reliable results while saving the customer time, money, and energy. Accurate results. Again, we're always starting with the finest screen first, and we only use 1 screen at a time. We want to remove all the fines first, so this eliminates any potential for agglomerations or cohesion. The more sieve screens used, the more accurate results you will achieve. Features of the MAJSX. It's a compact design, and it's very easily movable. The computer has touch screen controls. It's capable of using different diameter sieve screens. It has a quiet operation with a noise level comparable to a household vacuum. It's a clean operation. This is for maybe customers with potent materials. It's a no-dust operation, so it protects your operator. It's capable of communicating with a balance, and there's printing capabilities as well. These are screenshots of our easy-to-use software with step-by-step instructions so that any employee can use the MAJSX. As you can see here, this is where your screen size is shown, the sieving time, the time that is remaining, and the water pressure. Please note, the machine will not start until the desired water pressure is reached. Again, very simple, step-by-step. It tells you exactly on what you should do and how you should do it. This is what your report page on the touchscreen control will look like. You can choose, again, going back to the 2 mathematical models we discussed earlier in the presentation, the Rosen-Ramler or the log normal. These will help you define the particle size distribution range. Once you select print, this is what your print will look like. Once it is printed out, again, this is your complete result from your graph to the sieving time, the vacuum pressure, the weight before, the weight after. Everything is very simple and easy to use. A typical setup of your micro airjet sieve. You have your balance, which will communicate to the MAJSX, and then you have your cyclone. This is an optional feature. It is used to collect and reuse and reanalyze any particles 10 microns or higher. It has a 98% efficiency. Again, it is 10 microns or higher. And then you have your vacuum, of course. This is an example of what the cyclone attached to the MAJSX would look like. Of course, we have your balance. And then we have the two of our options for the vacuum that also come with HEPA filters. There are some limitations when it comes to dry sieving. Some sample properties have hygroscopic tendencies, such as coffee or cocoa, or some other properties might have electrostatic tendencies, such as silicone or Teflon. And these can provide a lot of analytical difficulty, especially when using the smaller test sieve screen. Sieve analysis also assumes that all particle shapes are round and will pass through the square opening. For long and flat particles, sieve analysis will not yield as reliable. This is because if you have a long particle that presents itself on its side to the screen, it won't pass through, and this is skewing your results. For material finer than 20 microns, dry sieving can also produce significantly less accurate results. Suspending the particles in a solution to transport the fine materials through the sieve screen might prove much more efficient. This brings us to wet sieving. Wet sieving's common uses, again, for any materials that must be analyzed in a wet state, or any materials with properties that are sticky or cohesive materials. Wet sieving technology. It's the same process as dry, except instead of air, we're using water. A rotating nozzle will spray a solution across the sample and disperse the sample across the tested screen. The liquid is sprayed until the preset time elapses or until the discharge water is cleared. While the nozzle is spraying the solution, an intense vibration is happening on the tested screen, which is forcing breakup of material that might film or block the tested screen. And it will also deglomerate any material that is stuck together or is very clumpy. Once the sieving time is completed and your sieving process is completed, you're going to have to dry the sample and weigh it to see the amount that has passed through or the amount that was retained. Again, before the sieving process, you're going to have to weigh the sieve screen, weigh the sample, and then place the sample with the tested screen with your sample in the Viblette. As you can see in this picture, the rotating nozzle is spraying the solution and it's dispersing the sample across the tested screen. And 5 seconds later, you can see how much of the sample has passed through the tested screen. I'll show you before again, and you can see how much has passed through. The Micron Viblette, also known as the BBL, has many features. It's easy operated with a short analysis time. It's repeatable and accurate measurements. The electromagnetic sieve vibration that will eliminate any film buildup on the sieve screen itself. It's capable of using different diameter sieve screens. Minimum of 5 liters of water per minute will come out per minute. It's suitable for water or other washing solutions. There is an independent water flow, nozzle speed, and vibration controls. And if we go back, right here you can see where the liquid is entered in the diagram. And as you can see here, the independent controls. It also can measure material from 10 microns to 4.75 millimeters. Common wet sieving materials range from anywhere with carbon black to clay suspensions to sediments to high clay content to mineral fillers or any materials with sticky or cohesive properties. For example, like I said earlier, coffee, very hydroscopic. Going back to the 4 operational parameters that Hosokawa goes by. Sieve screen specifications. The integrity of your sieve screen, wet or dry, is the most important operational parameter. They should not have any mars, dents, waves, or imperfections in them. These can skew your results. Hosokawa's test sieve screens comply with ASTM E1109 standards. They are serial numbered and certified to be at a specific level of compliance. Hosokawa screens are supplied with a histogram and a certificate to confirm that level of compliance. They're made of 304 stainless steel frames with 316 stainless steel cloths. In the stainless steel wire cloth sieve screens, we offer them from sizes of 20 microns to 4.75 millimeters. And we also do offer nickel edge screens from 5 microns to 45 microns. All screens are offered in a 200 millimeter diameter, 8-inch, or 63 millimeter diameter. These test sieve screens right here use our 63 millimeter diameter sieve screens. This is known as the MSA, or the multiple sieve screen adapter. This is useful for samples anywhere from 0.5 to 7 grams. It's very small. You do get, 3 results at one time. However, since the sample size is so small, it might not have the best representation of your distribution. Dry and wet sieving might not always be the best answer to your particle size analysis. The sample characteristics and the properties will determine the technique that you're going to use in order to produce the most accurate analysis. If you're unaware of what method will work best for you, or what method works best with your material, please give us a call. We are more than happy to help you with it. Overall, we discussed particle size distribution, and that's determining the range and size of particles in a material. We need to know this because it saves time, money, energy, and resources. And it produces accurate, reliable results, and that's what we really need. We went over pneumatic sieving, which is airflow that pushes and distributes the sample 100% around the test sieve screen so that 100% of the sample can come in contact with the screen. We went over the 4 operational parameters that Hosokawa feels best, that will help you feel best to get those accurate results: wet sieving, test sieve screens, and other particle size and methods and techniques. And this is my contact information. If you have any questions, please do not hesitate to contact us.